All right. So Rafi said we are going to talk about QSD, but sorry, Shannon. See, I'm not awake yet. But actually, we haven't finished talking about quantum field theory, and also, I mean, shadow body is just an extension of quantum field theory in the sense that it is quantum field theory for a specific gauge truth. And we're going to talk about what those terms that what is a gauge to, where does that come from, and so forth, right? So let's continue on that journey. Starting with, as I said, we want to know what the age theory really is. And starting with that, we talk about Maxwell's equations. So Maxwell's equations, describes classical electrodynamics. And with no source of present, everyone knows what the Maxwell equation looks like. We have the Lagrangian. Well, probably you don't know this structure, but there's the Maxwell Lagrangian or electron Lagrangian. And this is just minus 1 over 4 F nu F u. Now, if you remember what the Lagrangian is, it's basically T minus C, kinetic energy minus potential energy. And you notice that whenever you have derivative, product of derivatives, there is a kinetic term, and then any other term is a potential, the mass term or maybe a perturbation. You clearly notice that there is no mass term there, and that's a giveaway fact that the electromagnetic waves were not described to have mass. Right? So the Lagrangian, it makes sense that it doesn't have mass term in it. What is F nu F u do? Well, this is known as the electromagnetic field tensor, defined in terms of the order A u. Now, where does this, where if you're setting up your F u mu, electromagnetic field tensor basically mixes the components of the electromagnetic wave. So your electric field component as a magnetic field component, you combine them together, mix them together, and you have a nicer object, which is the field tensor. In the field tensor, some components are dedicated for the electric field, and the others are dedicated for the magnetic. So you have this big, large matrix that encodes all electric and magnetic fields. So that's what this field density is. Right? So we call it the Weak step. And AU, as I said, is a vector, so it's a vector field, and it's massive. And there are 4 components. You have 3 components of A as a 3 vector, and then 1 component which is the 0th component. And the 0th component usually is I, which identifies with the scalar field, and then we have a vector. So this scalar field is actually the scalar potential, and this A vector, 3 vector, is then the vector. So we are formulating electromagnets, and not in terms of usual forces. We're actually turning the tables where defining electromagnetism in terms of potentials first. All right. So it turned out if you have the electric field expressed in terms of the potential like this, and the magnetic field also in terms of the 3 vector A at the kernel of the 3 vector A, and you use this and plug it into your Maxwell's equation, basically it solves the Maxwell's equation very easy. Okay, and the next question to us is that then how many degrees of freedom does this massless vector use? Does anyone have any idea how many degrees of freedom can it have? Okay, good. Well, it has 4 components, so the idea maybe is 3 here and 1 here. So maybe 4 degrees of freedom. But what is really A encoding? A is encoding the electromagnetic field. What is the degree of freedom for electromagnetic field? It has 2, right? It has 2. So where does the other 2 go? Like you would take it as quarter, but I mean, where does the other 2 go? Well, the thing is, there are some gauge symmetries that will convince you that I will try to convince you that this actually has 2 degrees of freedom. So let's see if we can unpack that. See how. Well, as I said, by something called the gauge symmetry. Now, what is the gauge? What is a gauge symmetry? Well, the gauge symmetry is and the predominance in the theory that the potential is not strictly defined. It is quite arbitrary. Okay, and the arbitrariness of the potential is telling me that okay, I can shift the potential like this. I can shift, sorry, not potentially. I can shift this A nu, by derivative term with this parameter lambda, which depends on the space side coordinate. And the result of this transformation is a gauge symmetry is then a transformation of this AU field. And the result of this transformation for any function lambda x is that the f mu nu, you plug instead of a nu here, you plug in this big expression for the transformed AUs, and you get the same tensor back. So the electromagnetic field tensor doesn't change under this symmetry. So we say that electromagnetism has this gauge symmetry such that you shift a nu by some polar derivative, and that leaves this invariant. So is this a space-time symmetry? Yes, because lambda depends on x, which is a space-time coordinate. But this is also internal symmetry of the field. Okay, because the field is kind of undergoing some kind of shift, which leaves this f mu u invariant, which then if f mu u is invariant, then your Lagrange also invariant. So leaving your equation. Yeah. So this is basically the gauge symmetry. Yeah. So it's basically the same case. So basically you shift AKU by this parameter film derivative, then it leaves f mu nu unchanged. You see the Lagrange unchanged. You say that it's a gauge term. And this is the gauge transformation. All right. So then what does this mean? Well, I've said what that means. Basically, you look at your gauge transformation, you see, okay, lambda depends on x, but how many x's do we have? So this is fixed and important. So if you have a field, so AD is a field, so you then have infinite, or like the field is error, right? So it's infinite x's, right? So then that should imply that you have infinite number of symmetry. What you think about? You have infinite number of x's, all of the lambdas are dependent on individual x's, so then you have infinite number of symmetries. If you have infinite number of symmetries, these are all continuous because it depends on free time. So then, by Nazrul's theorem, we know that you have a complete symmetry, then you have a conserved current or a conserved quantity. So that should mean really you have infinite number of conserved quantities. Well, thankfully, that's not the case. We don't have infinite number of conserved quantities because this symmetry is not really a symmetry. Even if it's named a gauge symmetry, it's not really a symmetry. And of something else. So if you remember global symmetries, like for the scalar field, you could shift the scalar field by a phase factor e to the something I lambda or whatever. That lambda did not depend on the x t coordinates or space-time coordinates. Then that means the old system was transformed to some new system, which is very similar to the old system. But actually, the two systems are separate. They're independent, like in a sense that one is a new state, and it's transforming from the old state, but they share properties. That was the idea of a global symmetry. But when you have a gauge symmetry, basically the transformed state is actually the exact same state as the old state. It's not really undergo any change, right? So it's not producing a new state. It's basically just the same old state. That's the idea of gauge symmetry. So this comes from the redundancy of AU, arbitrariness in AU, that you are essentially building the same state by transformation. You're not going from one state to another with similar properties. You're basically having the same state reproduce itself under this case symmetry. So this is not in that sense in the sense of a global transformation. So then, so this is the reason why you don't have an infinite number of conserved quantities, because this is not really symmetry in the concrete sense of it. Anyway. So there are many gauge choices. So once you have a gauge transformation, that means you can define your theory. If you can define your theory in different gauges. Gauges are basically hidden descriptions, how you can express your AUs. And the choices to us may be Coulomb gauge or Rorensky and so on and so forth. So whenever you choose a gauge, you basically simplify the calculations that you are doing, right? It depends on what you are trying. So you think that the most important factor to Hudson field theory would be to protect our Lorentz symmetry or protect our Lorentz invariant, right? So in this gauge, the Lorentz gauge, the Lorentz symmetry is completely protected. come from. All right. But if you choose the Coulomb gauge, then you'd use the Lorentz symmetry to recover it some other way because your alternate theory must be Lorentz invariance. So basically, you pay the price at the beginning once you go to the Coulomb gauge, but then you have to do some manipulations to actually protect your or reproduce your Lorentz symmetry for it. So it depends that what you want to do really. So this sometimes simplifies calculations, and this sometimes has involved many calculations. So maybe sometimes this is easier to do that, and then you go and protect your symmetry. Yeah. No. This is combustible electrodynamics. So you can do classical electrodynamics. You can do states and different gauges will give you like how you approach the problem, but they should give you the C.
To gauge the fusion, you got the uh piece of radius the fusion equals. Also,
Well, I'm not very well versed in the technicalities of the math terms, but maybe like the equiomorphism is an idea of reparameterization. So you're reparameterizing your theory under which uh, theory using variate. But I had not really thought about gauge transformation to be as a similar to equiomorphisms. But maybe and okay. So then basically you have to make a choice depending on what you need to do. All right. So let's choose some choice. Let's make a choice. We say, okay, let's go the Coulomb gauge. The Coulomb gauge on this is that the divergence of A is 0. That means this is a constraint on the 3-vector part of A. So that means this gauge choice automatically fixes the fact that all 3 components has one constraint. They can't have any divergence. So that means you have 1 degree of freedom that's left untouched, and then 3 that is going by the same condition. So you have basically reduced 4 degrees of freedom into just 2. 1 for the 0 component and 1 for the 3-vector A. Right? So that's how you end up with 2 degrees of freedom. All right, good. Now, interesting things happen when electromagnetism couples the matter. So we want to look at X at this point. So that was Maxwell's equation in vacuum. Now we introduce some source error, right? Some kind of disturbance in field, and your Lagrange changes by a term. Let's say it is term. So this is the kind of source term, the potential energy, right? So then this produces the Maxwell's equation that we got inhomogeneous source term from the right side. And this kind of we could take the partial mu J mu that gives you the non-homogeneity equation that signals are constant, right? Constant current. And Ju is a constant current. And we're interested matter coupling with electromagnetism. So matter like 2 kinds of fields, scalars, and also so far fermions, which are spinors. So if you're talking about fermions coupling to electromagnetism, well, first let's write down the corresponding Lagrange that fermions go by. So we have the Dorado, which basically is kind of spinor fields, and we are seeing that CX are getting very big here. And this has a U1 symmetry. So the U1 symmetry here is that you can make a phase shift in psi and psi bar with this stage factor, either I alpha into the minus psi alpha. And under this phase shift, this constant current is this term right here, psi bar gamma nu at psi. So the theory here is basically the Lagrange doesn't change if you made this kind of shift in the size. Okay? And a probability to verify it on a free time, and you're going to explain and whatnot. Verify these 2 things. Plug in psi. Instead of psi, it's psi bar here, plug in this thing. Instead of psi here, plug in this thing and see if your Lagrange will make a change. Right? And when you include interaction in the magnetic field, you take your Dirac Lagrange and your electromagnetic Lagrange. And so this is the free electromagnetic Lagrange. This is the free Dirac Lagrange. and then you would make them talk to one another. So we have a new field talking to the spheres. So you have built an interaction graph, right? And this coupling here, that there's a coupling constant that kind of gives you this coupling between psi bars and psi's and ADU is E. And what is E? Electric charge, right? Okay, so the question to ask then that we have built this Lagrangian of the fermion fields or scalar fields interacting with the electromagnetic field. Is there a gauge symmetry to this Lagrangian? Well, remember what a gauge symmetry. You have U1 symmetry. It is a global symmetry. The gauge symmetry is basically the global symmetry with the parameter that you're describing your phase with, depending on x, depending on space-time coordinates, right? So then, what kind of gauge symmetry can this Lagrangian be tested for? Well, it has FU unit. FU mu has a gauge symmetry. We talked about it in the first slide today, which is basically a shift in F mu mu's. And then we're now talking about also another, which is the Dirac constant, and it has a global U1 symmetry. So the idea is maybe it can be tested for the local virtual. It's another gauge symmetry. So whenever you elevate your U1 symmetry to being local, you have by depending your parameters on x's, you get a local gauge symmetry, right? So the idea is we have to see if this works out to make this invariant under a gauge symmetry. We have to introduce a new kind of a derivative which will replace this older d mu's and d u's inside the active u's with this derivative. Yeah. Okay. So this is a covariant derivative, and covariant derivative introduces an extra term. So this is the regular derivative, right? Regular derivative is just this partial u acting on psi. But then for the derivative problem, your derivative needs to change with an extra term. Why? Because L is invariant if and only if you have a shift in AD mu's and also a shift in your size with parameter depending on space time. And the symmetry is encoded in the fact that you have to change your derivative definition. So instead of using ordinary partial derivative, you kind of have to include it with an extra term. If you use partial u's and just introduce the AU transformation and the psi transformation here, you would find that your Lagrangian has changed. It doesn't stay invariant. But to kind of extract state invariance of the Lagrangian, you have to redefine your derivatives by its covariance derivative. If you use instead of partial mu here, we use capital DDU, right? You will see that the Lagrangian is invariant. So you get the idea that you kind of may think to yourself that this is kind of artificial. I'm kind of changing one Lagrangian myself by introducing this new kind of definition for the covariant derivative. But really, AUs themselves are quite arbitrary, right? So this really does not mean that you are changing a theory. You're just basically being guided by your AU. Okay? All right. So there's gauge symmetry, which is a continuous symmetry again. So there must be a conserved current according to another experiment. And the conserved current for electromagnetic interactions with matter is electric charge. And electric charge is encoded in this constant of nature, which is the Instructor constant. If we plug in your 8 bars and these, and I think this is in SI unit, you get an approximate power 37, 1 over 137. So that number includes how strongly the magnetic interactions are. Okay, so how strongly sides and electromagnetic waves kind of interact. So this is the fire circle. Now, another matter of use that we have talked about are scalars. So can we use scalar terms and make them interact with electromagnetic field? Well, or a real scalar field. Do you think that's possible? Well, the real scalar field, there is no conserved current, right? Because real scalar field has only 1 degree of freedom, right? And there's no coupling to the gauge. So whenever there's no conserved current, that automatically means there's no local symmetry. There's no symmetry of the problem. Then there's no and the contract parent. If there are no contract parent, it cannot really couple to the gauge field. What is the gauge field? The gauge field is basically the AU. Okay, and so with scalar field, you not really you can't really build an electromagnetic pathway. With a complex scalar field, that's a little bit different because we have seen that complex scalar fields has seen yesterday we have seen complex scalar fields as you observed. So in that sense, whenever your theory has U1 symmetry, you basically can make it local by demanding that your transformation parameters, lambda or whatever, depend on your SY space-time coordinates. If they do, then you can always define a covariant derivative and then make your Lagrangian, write your Lagrangian equivalent to the covariant derivatives, which means the Lagrangian you stay variant under a gauge shift or gauge symmetry. Okay, so basically, the maximum Lagrangian, in effect, this Lagrangian. Okay, so yes, you can build a theory with a complex scalar field talking to your basically your Margie electromagnetism with complex scalar field. All right. So then the next step is this is all classical. The next step is you quantize your electromagnetic field using the prescriptions, the same prescription as we quantize scalars and quantize scalars yesterday. So basically, what's the process? You first elevate your functions or fields to being operators, and then you have to define certain variable, have certain other operators like conjugate momentum and whatnot. Those are expressed inside the ladder operator, and those ladder operators operate on the field, give you kind of excitations of the field, the excitations of the field for spinors that are fermions, and then for the scalars, there's then your other fields, and for this one, the excitation will be what? Of course, the excitation of the electromagnetic field is a boson, right? So the photon would be the product of electromagnetic field. All right. So we're not going to go over quantizing your electromagnetic field because essentially they're the same process with suddenties and latic altitudes. But on the face of it, we're not doing much different. Canonically, the process is kind of very streamlined to the output. All right. So now we have quantized electromagnetism, the quanta of electromagnetism is the photon. So the next step is quantum electrodynamics, right? So after we have quantized electromagnetism, we want to see if the interactions between the fermions and the electromagnetic photon are what is the quantum theory of that? So this is the quantum theory of electrodynamics, QED. So the Lagrangian, if that defines QED, this Lagrangian here, you have the Maxwell Lagrangian, and you have this Dirac Lagrangian, and the quantized picture of fermion and light fermion light interaction, basically what we call QED. Okay, and you have your gauge symmetry. So the gauge group is U1. So that means it is U1 local symmetry. So under U1 local symmetry, your Lagrangian remains invariant. And this is what we call an abelian group. So what is an abelian group? Anyone? Right. So we talked briefly about groups yesterday. So groups are basically kind of structures which have with a multiplication rule attached to it. So you can, if you have two elements of a group, you multiply them together, you get a product as a group that also makes you. That's basically what a group is. So there can be different types of groups. Abelian groups are the easy groups. Abelian groups, we have the group of elements from the file. What does that mean? Well, if you think about rotations, right? Think about rotations, what kind of group they are. Just try and rotate whatever you have. First go like this, and then you go like that. Okay, first I rotate like this, and then I rotate like that. Now I reverse the order of, right? If you reverse the order of this, you end up in a different rotation. So the order of rotating your object was important. You don't get the same thing at the end. So there's an example of a non-abelian group. The action don't commute. If you do first one thing and then the other, you end up with different results. But abelian group, then must have the opposite property. If you do opposite kind of measurements, they don't really affect the islands, correct? So that's the group elements, and they kind of commute with one another to update behaviors, right? So what kind of interaction that we're talking about here? We're talking about interaction between fermions and like the quantum of light with the photon and photon with the fermion in Heisenberg diagram are basically wavy lines, right? Solid line with arrows on them. We have seen are fermions with phase arrows go the other way in time. They're anti-fermions, and wavy line are your pull. So this is kind of electron coming in, a positron coming in. Electron, positron talks to one another with the photon field, and photon, and then they, right? So basically, this is electron positron ionization, and you can also kind of topologically rotate this, and you get similar process to the different diagram. You can also scatter off electron the muons. Electron the muons come in. They talk by mediating a photon, and then they go in their separate directions. So these are kind of interactions what we see quantum electron. Okay. So yesterday we saw interactions of fermions with scalars, and we have seen scalar interaction. Here the vertex interaction. Okay, this fermion, another fermion, and then you have a photon. All right. So this thing here, this part of the diagram is called the primitive vertex. Basically, two fermions interacting via the photon. Okay. So this is a three-level diagram. So there is no loops inside. So there are only external lines of the diagram. We call these diagrams three-level TBD. Right? And so this is not, of course, a total story. We have seen loop diagrams before, because basically, if you do perturbation theory, you want higher and higher order current in your perturbation. So that makes your diagrams kind of curved in a way that you can introduce internal lines, more internal lines, and more vertices. So these internal lines are virtual particles. So virtual particle and real particle. The difference is, in experiments, you only detect the outgoing things. These are real particles that you can actually see and measure. Inside, whatever happened, you don't really see. So if your calculations give you imaginary mass for inside particles, that really doesn't matter in the sense that you're not really observing imaginary. As long as your observables are real and finite, you're good to go. All right. So these are the real particles, and these are the virtual particles. And we don't ever see virtual particles. We only care about the real one. So you can have many different diagrams and thermal. So that will give you higher order graphs. So this particular diagram is called a vacuum polarization diagram. Basically, give you this loop. Okay. And the loop is basically, particle and particle basically talking to one another. And then at the end of these loops, you have photon. Right? So if you apply your Feynman rules from yesterday, you can actually calculate the diagram. We actually saw, I think, one of the diagrams with a loop in it, and we found that it had some infinity. The EW was infinite. It was logarithmically divergent. And to get rid of this, we introduce a high scale cutoff. Basically, we demand that our theory is only consistent of some high energy value lambda. And we get the coupling constant of theory to be a function of that lambda. To be a function of that high scale. We are defining, right? So in that sense, we can say that the coupling constant is really not a constant. It changes with your energy. So the higher the cutoff, the more different your coupling constant is. So it depends on what energy you're extracting the value of. The coupling constant is not really a constant. Rather, it runs with the energy scale. So the higher you go, the more it tends to run, and then you extract a clear width scale, as let's say 1 p. Okay. So this leads to your amplitude depending on your coupling GE, the usual three-level coupling. But then when we define lambda chaos, the high energy cutoff, the amplitude now depends on this GR. This GR is the renormalized speed. This process is not the renormalization we talked about briefly yesterday. So this sapling basically will be the amplitude now depends on the renormalized coupling, and the renormalized coupling is approximately is renormalized coupling. The amplitude is essentially a function of the inner minute, whatever you're integrating. But that is quite problematic because you want this to go away, but it turns out that this depends on you. Well, this is another remnant of the fact that your normalized coupling is dependent on momentum. This is core momentum. Core momentum means it has both energy component and then you have your free momentum component, the spatial momentum. So then what this is saying really is your coupling actually is dependent on energy. So then electromagnetism, I'll let for a brief moment think about flow interaction. So if you have two electrons, this much far apart, this have they have stronger interaction than when they're this close apart. So which one is stronger, close or far? If you think about Coulomb's law, 1/r, so the farther you go, the weaker the force. So then if you have two electrons very close to one another, then you have a stronger strength of the electrostatic interaction. Here, then that means the energy scale will depend, the momentum will define the energy scale, of course, because it's all momentum. And the higher the momentum is, the closer the two particles can get. So the closer the two particles can get, the bigger the coupling would be, right? So that's the idea of a running coupling. Okay, so this is the running coupling, and basically that comes out of the fact that you're cutting off your theory at some high edge. And so effectively, what we actually measure for the electromagnetic coupling in experiment, we are not actually measuring a constant, we're extracting a running depth. We're extracting something that runs at the scale, and then we extract out what we eat and what we observe at our end. So essentially, this the electromagnetic coupling is not a constant, right? So effective electron charge is basically calculated from tree-level diagram, but also has contributions from loop diagrams. So all of the amplitude, however many loop diagrams they include, they have smaller and smaller correction. So more loops means more vertices. More vertices means more factors of G, but G is a small number, 1/137. So the more powers of G you have, the smaller the number becomes, right? So the higher diagrams becomes less significant as you include more and more vertices and more boxes and more loops, right? And so effectively, this kind of a diagram, the vacuum polarization, is screening and of shielding the raw electromagnetic coupling, right? Because the raw one comes from your free-level coupling, but any process we have these higher order loop diagrams. So essentially, what you measure is not the tree-level coupling at all. So we're measuring something at different energies. We may measure different of the electromagnetic. But that's a problem because then you say, okay, then how did Coulomb just write 1/r squared? Like, why was it squared? Okay, the only thing it depends on is the distance, nothing else. Because, at the quantum level, he didn't know anything about quantum mechanics. But at the quantum level, we see that the coupling is not really a constant, only depending on distance. It also depends on the energy, the momentum of the two particles. The thing is that non-relativistic energy, this factor, it is going to be very, very minimal. So if your momenta are not relativistic, then you are fine. The laws of plastomy. Okay. But higher and higher speeds, relativistic energies, then you have to account for a running coupling. So at the quantum field theory, we have the running coupling. And essentially, you're measuring GR, the renormalized coupling, and not GE, the tree-level coupling. So this is the idea that we make electromagnetic coupling may be log divergence, maybe go up to infinity, but we don't really measure anything because we can't go up to arbitrary high scale that extracts our observable energy that. So we actually extract a renormalized coupling. Right? So this idea is due to be work. This is the first theory that fundamental advanced splitter kind of normalized, kind of uh, concretely brushed away any activities that appear, because by the argument that we are not actually measuring anything infinite. So this is the idea of renormalization, and this poses a lot of things for the next theory we're going to discuss. But till now, first. Strong calm. So, or the electromagnetism or strong force. Strong force. We'll talk about strong force. Yes. So we'll talk about QCD right now. So clear that. But yeah, that idea is that they're okay. QCD is. Yes, because basically Python diagrams are at the point where the fields have already quantized or given you excitations before. So yeah, fields are actually the ones interacting, but then these are excitations of the field. So yeah, you get boil it down to particle interaction. So that's how they're reacting. Particle physics at EK. It's like you slap you. It is quite. Yeah, time dot and field. If it's a real scalar, then you know not really illuminating. When you make it into a complex scalar field, then it becomes important with a one. But real scalar field, you cannot alter it. All right, now we have discussed QED, which is the theory of fermions interacting with electromagnetism. Now we go and discuss quantum chromodynamics, or QC. So chromo comes from the Greek word color. So color is going to play a part uh, in this uh, in this process. So we're talking about incredibly small things, fields and particles that are incredibly small. And imagine your electron or your proton coming in blue, red, and green. Doesn't really make sense. Blue, red, and green are electromagnetic spectrum that we visualize. If you can visualize color, then why can't we visualize the particles that make up the proton? Well, the answer is quite simple. Those colors have nothing to do with the color of the rainbow, but has everything to do with the idiosyncrasy of the linguistic, right? So we define something like color, you have nothing related to color, right? So that's going to play a role in what we call that. So this is a QCD Lebanton. The QCD Lebanton we had, this looks like the bureaucrat around him, and this looks like something new, but it looks quite similar to the electromagnetic right? So this is actually a physiogenic tensor, which we had also for electromagnetism, but this is a different G. What kind of field that can be? G. So it turns out this capital G denotes something else. So let's identify these things. Size are spinners. Now these spinners define work fields. So psi is the work field, and psi bar is then at the work field. And this G, capital G, are a gluon field strength tensor. But what is a gluon? Well, gluon is the excitation of the gluon field, and gluons are the particles that mediate strong interaction that holds the nucleus together, the hadrons together. So this is a first quite similar to your electroelectric heat tensor, and then you have these terms, more terms. The electroelectric heat tensor at two terms, it has one more term, right? So in here, the they use in the field tensor equal to area potential and the vector. So here, this AU field is the gluon. These are the gluon fields, right? So G mu nu encodes the gluon field, right? So the A's are gluon indices, counting the number of gluons in your theory. And it turns out there are 8 gluons in your theory. And so there are 8 gluons, that is, there are 8 mediators of strong force. In electromagnetism or QED, we had only one mediator of the electromagnetic force, which is the photon, right? So this is just by having 8 gluons, this immediately seems more complicated. More mediators, then they require that QED, so this is more complicated. And this took a lot of effort on this, okay, to really read on like. So, yeah. So as a descriptor, basically the generator of group and what it is, how can you also. All right. So QCD is the quantum theory of the strong interaction. QED was the quantum theory of electrodynamics. And the gauge group that QCD is defined in is SU3C. The C in the bottom identifies color. So we say that SU3 gluons are charged under color. So this SU3 is a representation that is calling we are calling SU3 up, right? So where does this color come from? Well, color is the conserved charge for strong pairs. Okay. So this is a not abelian group, and we have already discussed what an abelian and a not abelian group is. So QED is abelian, that's easy. Non-abelian, not so much. So that's why it took a lot of effort by brief minds to actually renormalize it here. All right, so the primitive vertex of QCD is this interaction. So you have quark interacting with the duon and then quark going away. So this is not a process tree, it's just a primitive vertex. This is not going to be a process. So this is a process. So you have a quarks coming in, talking via a gluon, and then going their separate direction. So that's one interaction that you can have. But you can also have something like this. You can have an electron positron annihilate via a photon that gives rise to another electron positron pair that move away. That's one process. But however, this QED process is kind of can be connected to a QCD process because if the energy of the abelian is big enough, electron positron can annihilate to give you then quarks. So this QED process kind of gives you a way forward into QCD because quarks are explained by QCD. So then this theoretically implies that you can see quarks in acceleration, right? Because you're producing quarks in the ion state. So there's no reason why you shouldn't see quarks in acceleration. But the curious fact is we had never seen a quark in acceleration. Okay, so we let's see proton, let's see neutron, but we can work on the neutron. But protons and electrons are themselves made up of quarks. We had never seen quarks. So how do we know quarks exist? Because highly likely that quarks exist. Number actually get points to say that they definitely exist. But all of our theories say they exist. So we take it. Okay. That's good enough for us. Okay? But then what happens here? Where do these quarks go? You don't see them. Where do they go? Well, that is the idea of what cycles will be good. For the next question, the idea of quark confinement. So these quarks want to fly apart. So they start flying apart. So you have a quark and anti. So the quark and anti-quark wants to fly apart. But the farther they go, here's the positive factor of QCD. The farther they go, the stronger they interact, which is quite insane. If you have two electrons far away and two electrons closer together, there is a stronger interaction than that, right? But QCD quarks are telling you the exact opposite thing. The farther they want to go, the more strongly they want to interact. So basically, they try to run away from each other, and then they do all the interactions. Don't let them do it. They want to bind them together. It's like Sauron wanting to bind everyone into the dominion of one ring, right? So basically, these gluons are Sauron, the corruptor. And so basically, they try to fly apart, but the gluon interaction mean that the quark zone interacts via gluon. They produce more quarks, and then this anti-quark produces more anti-quarks, and then quarks and anti-quarks annihilate via gluon, and you get multiple of the kind of diagrams, and they end up in jets. So when you collide two hadrons, you get a lot of jets in your collider. So if you Google NHC image, you will see a lot of things flying apart. those things are mostly gluon jets. Okay. Oh, no. I think nobody knew. Like, so this is a mediator. We use Feynman idiosyncrasy. Use wavy lines or photons. Okay, so photon is a mediator, gluon is a mediator, so they must be different. So let's just use rays. So that's the interesting thing about UCP. UCD, this idea quark confinement, and this is related to this big fact that your question now raises. He asks if they get closer together, do they repel or something else? Interestingly, the answer is no. So QCD is kind of Gaussian, right? So farther away, they interact very strongly, binding into that one ring thing, but closer together, they will be talk to each other. How crazy is that? You want to live with some person, when they go farther away, I say, oh, don't go, I will die or something like that. But then you find them, bring them to your house, and you never come. That's insane, right? Those are basically ports, right? So that's insane. At QCD, it is insane. Like people are insane. That. Okay, so this is the idea of quark confinement, and this relies in the fact that quarks and gluons, both of them are charged on their color. They both have color charge. In electromagnetism, our photons charged. By charge, for electromagnetism, I mean electric charge. Photons don't have an electric charge. So basically, photons don't have any interaction with any other photon, right? But in strong interaction, gluons carry color charge. The quantity, the conserved quantity that they group, where is it? Here, the group SC3 charge under. So basically, quarks and gluons are very similar. So gluons will also directly flow. So that means immediately, you will have more complicated situation. And this will play a big role in shaping what PCB is. And in any strong interaction, the color is conserved. So for example, you notice it's red, blue, and green thing. It has nothing to do with regular red, blue, and green. So these are just wavelengths that you're not seeing. However, using this as a physicist, the color charge is R, B, and G. So we define color charges. So gluon can be either red, blue, or green, or combinations of the two. A quark can be the red, blue, or green. So any strong interaction, the color is conserved. So basically, a red quark, let's say, comes in, a blue quark goes out. The difference in the color is taken away by the gluon. That's our color conservation theory. Okay, so this is possible because gluon themselves can carry color. It's not possible in the electromagnetic. You can't have charge non-conservation like that with a photon. Okay, and the coupling constant between two protons is, let's say, greater than 1, right? And we are measured in the laboratory. It happens to be if you have two protons, they're interacting. The coupling constant happens to be greater than 1. So then, the coupling constant usually we think of as a three-level diagram. However, in electromagnetism, it is easy. You take a three-level diagram, and then you take loop diagram. The loop diagram wants you to do less and less because G is a small number. You have higher powers of G, you get more small number. But here, the three-level G is bigger than 1. So if you have higher order loop diagram, you have bigger powers of 1 square, cube, whatever, you have bigger number. So then the amplitude kind of blows up. It gets bigger with more loops. So then you keep on drawing kind diagrams till it's fine, and you gotta get done. It's all that, right? So that's the problem. And it seems like it spells the end of QCD. If you can't treat QCD for primitively, like higher order things get smaller, then there's no use of, right? I mean, we can't really theorize in our quantum theory set. So that was a problem until something known as asymptotic triangle was discovered. So this asymptotic triangle, what is? Well, you look at the vacuum polarization diagram. is very similar to the diagram we had in QED. And instead of the photons here, you just have the gluons. But here they may be the orchids. Doesn't matter. Okay. So this is a vacuum polarization diagram, but then you also have diagrams like this, or many more, which you never had a QED. What do I mean by it? Well, these are all gluons. These are all gluons. In QED, you never have all photons there in your internal lines because photons don't interact with QED with each other because they are not charged electric charge. So to be interacting with themselves, they need to have that charge under which the group is charged. For a QED, the group was U1, the conserved charge was E, but the photon was uncharged. So it does not accelerate interact. But the gluons are charged under the color, right? So they themselves interact under strong interaction with strong interaction. So if you have a vacuum polarization diagram with quarks in it, you might as well have also gluon vacuum polarization diagram. But that makes the situation more complicated. And you see why when you notice that your gluon bubbles are unique to QCD, but what is the role of a bubble diagram, loop diagram? You can see in QED that the role is basically to screen the real coupling, right? So it screens the real coupling, but then these other diagram, this would screen the QCD coupling, the real coupling, the vertex coupling here. Basically, if you were thinking about QED, if you only have these sorts of diagrams, the more loops you have, it will kind of lessen your amplitude, kind of squeeze down your coupling. However, due to the presence of these have the opposite effect. So these screens the vertex coupling, but these anti-screens the vertex coupling. Okay, so the gluon loops kind of do the exact opposite to quark loops. Okay, so then automatically, the more of these you have, the bigger your coupling becomes. So the strong coupling, the only way I can tell you to be certain what all of this really means is to look at the expression how you calculate the gluon coupling. This is the strong coupling alpha, depends on Q squared, which is very scale. And this is a complicated looking expression, but don't worry too much. You don't have to memorize this and write it on an exam or something. We have two important terms that we want to look. This term and this term right here. Okay. So what is N? Well, N signifies the number of colors that quarks and gluons can carry. Quarks can have. So quarks can carry three colors: red, blue, and green. Remember ours, these are nothing to do with the electromagnetic spectrum. Those are names that will be in charges of strong interaction. So this is, we have three, right? Red, blue, and green. And we have 6 flavors of quark, 6 different types of quark. Up, down, top, charm, straight, bottom, right? So we have 6 different, 6. So then this number, 11mi square, what is, well, 11n is greater than 2f, right? Because 2 times 6 is 12, and 11 times 3 is 33, right? So then this number is positive, right? If this number is positive, then it has some implication. If this number is positive, then this is a big number, but then this big number gets multiplied to a logarithm of 3. So the higher your cutoff is, this denominator kind of starts going up, right? But if the denominator goes up, then what happens to your coupling? Well, it should go down, right? Well, 11n greater than 2f, the coupling actually weakens with increasing energy. So you have bigger energy. This is greater than 1. So your bigger energy, denominator goes out. That means your coupling weakens with increasing energy. So increasing energy just means short distances. If you're zooming in with very high energies, you're actually zooming in a very small scale at the size of inside a photon or something, right? So if that's the case, then that should mean if you have 2 quarks very close together, their coupling is incredibly weak, right? If their coupling is incredibly weak, they don't really interact at all. But then whenever you try to pull them apart, they start interacting much strongly. So that's the idea of work confinement, where work confinement comes from. And this is quite weird because usually you think you bring two interacting objects close together, they interact or something. But this is a weirdness in QCD, and this is known as your asymptotic field. So it turns out that inside the proton, quarks are almost free. They swash around, whatever. So you think, okay, it's easy to, I guess, see quarks. But, whenever you try to pull them apart from the protons and neutrons, they all say you want to do that, right? So they're confined to be inside the protons and the hadrons and the mesons and whatnot. All right. So with increasing distance, the coupling gets large very rapidly, resulting in quark confinement. This weird behavior of the coupling constant that it lessens with shorter distances, well, that is the idea of asymptotic freedom, which was explained by Pulitzer, Gross, and Lichter. And they discovered this asymptotic freedom in 1973, and they won the Nobel Prize in 2004 for their contributions in UCE. So without this idea of asymptotic freedom, then quantum chromodynamics would be a dead water. Why, you say? Because now we look at this term, right? This is the coupling constant that's depending on nu square. So usually in the QED case, you have the coupling that and the zeroth order coupling, if which some terms were added or not. But here, this is not the zeroth order coupling because we really don't have a zeroth order coupling because we haven't really seen quarks interacting because we haven't really separated quarks at all. So all we can really do is start from an energy scale where it's large enough, where perturbation theory is applicable. Okay, so essentially, instead of starting from set zeroth scale, we kind of set our scale mu such that this coupling is less than 1. And from there, we kind of go and do perturbation theory. And that is made possible by this asymptotic freedom, this idea that QCD is different from P. Right. So yeah. Question. Well, the colors become apparent when, so this is not a strong interaction. So there's no color involved, right? So this is a QED process, the QED putative vertex resulting in quarks. The quarks have color, but then the color becomes apparent whenever gluons come in. So then quarks interacting with other quarks and gluons basically get you a color confirmation. So at this level, it's not really strong interaction. Yeah. It's basically rising in, like quarks are rising as a result of QED. But then when quarks interact, then you have colors. Then you have the essence of construct. Okay. Yes. We don't. Well, we have place limits on it. Basically, if you're inside the proton or neutron, the quark don't simply interact. So the radius of a proton or a neutron. I mean, the only physical interpretation that I know of is asymptotic free. I mean, that's how they explain it. Uh, but uh, but since we have not really isolated quarks, we don't really know for sure what's going on. asymptotic freedom was a dead theory, like took many years for them to win the Nobel Prize. People thought this idea was great, like small distances and things are interacting, yes. So this idea, like till now, is the strongest idea that we have about the small scale behavior of works. So yeah, like QCD is in that sense really difficult. So I don't know of any physical interpretation, like singularities or what. Are they? It's an open question. You were saying, um, the what do you mean by the cutoff energy? Like it isn't fading or what? Is so Q squared. So Q squared, yeah, depend on the energy state, right? So the lower it is, the smaller energy, meaning larger distance. Larger distance is more strong area, more confined space, not isolated space. So the denominator goes to zero when we have this series too small or too large, too small, right? So yeah, so that's why you pack off your period. You don't want like that thing to happen. So this is the active feeling that how you build that up. So every kind of part of theory so far, they're all hectic fluid theories that we example the reference. Yeah, that's the situation was really kind of famous. Yeah. Yeah. Uh, Whenever you try to basically we how do we know quarks exist? We know that are constant. We know that either nucleons, right? Nucleons are protons and neutrons. They're made up of three quarks each. Okay. And these are what we call hadrons. So nucleon. And then we have other types of quark anti-quark states, which are these, right? Q and Q bar. Quarks and anti-quark merge together to form makeup. So these are the things that we know that quarks make up, right? So then, um, so then, um, whenever you try to break up a measure and separate the quarks, very soon after you have broken it up, it forms another bounce state. So it's very difficult to identify what distance they have because the time before which you break up a bounce state and then another one forms so it's very difficult to identify any such distance gaps.
How does the take of sample electron is
Good. Range of the song course is basically inside the atomic units, right? Sorry? Yeah, I mean, so uh, the since the since the gluons themselves have color charge, they also exhibit effects. So they can't really move very crudely, if I say, they can't really move much before they go into another interaction. But the photon has no charge at all, so it doesn't interact with anything. So it only interacts with fermion. So the photons have a long range before which they go into other interaction. But the dual, their basic characteristic to be interacting inside the proton or inside the neutron and whatnot. So that's why you have the range that is so small for the strong nuclear force. But the photons are a big, large range because the photons don't carry electric charge. Okay. Well, no, this vertex has no coloring. This is not charged under cover. This is not charged under cover. This is not charged under cover. So this process is fine because this process is QED. And they start running away from each other what they can't, because as soon as they're produced, really, they directly blow up. And at these vertices, you have color. So this is incredibly short packet for that. So yeah, that's not a solid interaction. We don't worry about color. That's still a QE. I hate well, there is no decays involved, so it's most likely going to be pretty instantaneous because we have never identified any quartz in isolation. So quartz will maybe you can identify quartz tracks and whatnot, but we have not seen. We have just seen evidences of quartz in jet. So yeah, I think it's almost very close to. All right. So that's all of it. Okay, 5 minutes. Okay, 10 minutes. I started 10 minutes. All right. So we discussed this. So we had questions. Now, what is this? I don't know much. What is this? Right. So this is absolutely nothing. Literally, this is nothing. This is what people believing that. So essentially, what this is a quantum vacuum. In a quantum vacuum, particles can come in and out of existence. No worry at all. So vacuum we define to be empty. It's not really empty. It's still with these virtual parts. So I say virtual because we don't really detect any of them because they instantly come in and out of existence. So this is a GIF of absolutely nothing. But this idea will lead us into something very interesting. So this is the quantum vacuum, and this is related to the idea of symmetry rate. So in let's consider a massless chaos. So there is no mass term, it's always just the kinetic term. And let's do a shift in the field. Let's say phi goes to now 5%, right? So this is a small parameter. In just the case, you can easily check by inserting in place of phi, you just insert 5% epsilon, and you do the calculations. You will find that this is not dependent on space-time coordinates. So partial nu of E is 0. So that means you end up with the same Lagrange. So that's pretty easy. So this under shift of the fields, Lagrangian median parity. Now let's consider a massive scalar field, meaning you like tag along a mass carbon. Before a mass term, there is a minus because it's E minus Q for the product. So then you do the shift, you have some problems. You do the same calculation, right? You do the same calculation, but with this plug in 5 plus epsilon here, and you find offending term, the symmetry is destroyed. Because whenever you plug this in instead of this, the Lagrangian has an extra term which doesn't cancel, which is m squared pi squared. So this is an offending term. And if there are terms like this present in your Lagrangian, we say the symmetry of the Lagrangian, particularly this shift symmetry, is broken explicitly by the existence of this term. This is explicit symmetry rating. Okay? This is pretty easy to understand. You have an extra term, the Lagrangian, this does H. Sorry, H. All right. Now consider the potential. This potential. So this m squared, mu squared kind of similar, but I'm using mu squared for reasons that will become evident. So we basically, you take this Lagrangian, you add to that Lagrangian this potential. So you see there's a wrong sign for the mass star. Here we have positive for the mass star. Okay, so automatically you're getting something wrong with this potential. So then you consider this potential in this Lagrangian, and if mu square and lambda square is greater than 0, we can find how this changes. We can find the minima of this potential, and we'll find the potential looks like this, basically quadra. Okay, and the minima, the only real minima is at 0, I equals 0. So that's the minimum of the potential. That's easy. You can do very basic elementary school algebra, elementary school calculus to find the minima, which happens to be only real at phi equals 0. Okay, so this is the shape of the potential. All right. Now you do a phase shift. So you put this value of put this expression of b of phi into your Lagrangian, and then you do a shift of the fields in the sense that it's not field shift, but rather you invert the sign of phi. So instead of phi, you input here a minus sign, minus phi. You find that your Lagrangian restores the symmetry. There's no change in the Lagrangian for this kind of a shift, or this kind of a change in phi. All right. So this is symmetric. We said that the Lagrangian is symmetric under the texture change of phi and phi minus 1. Okay. Now things start to become very interesting at this point. Now we introduce another kind of transformation. It's not really a transformation. It's basically a variable with change. We replace mu square because we notice that mu square is the wrong sign. This is not really how we define a Lagrangian. The mass term must have a negative sign of 1. So then let's replace mu square with the minus in your V, and then you plug it into the Lagrangian. You get this order. Okay. So if you have a minus q squared, then you have t minus u, then you end up with the positive sign. So then you find that this is your potential, the potential that has a negative sign in it. And the potential, you can find the minima again for the potential by doing the same dv by d phi is equal to, right? Find what the value of phi. You find that your potential now looks like it has two minima. It has two minima, right? One here, one there. Now, imagine yourself living up here. You're completely symmetric about the mirror. So if it's the mirror, these two exactly look the same. You have a symmetry. But the moment you choose to either live in here or here, you have automatically broken that symmetry. This is the idea of spontaneous symmetry rate. Okay, so there are two minimas. You are free to choose any one that you want to live in. And thankfully, our cosmology calculus, we have chosen to live in the positive energy space of the vacuum, right? So whenever the lab, you're actually breaking symmetry, but this is not, the symmetry is not broken by any explicit clarity in the Lagrangian, but rather spontaneously broken because we have chosen to live or be in a certain lemma of the potential. So this is the idea of spontaneous symmetry breaking. Okay. So if the field settles at either vector, phi to phi minus phi stops being a symmetry of the problem. And essentially what we have here is spontaneously broken symmetry. So in cosmology, we think that after the Big Bang, there was a phase, a quark phase or something like that, quark epoch, where the potential looked like this. So everything was at a nice mid, everything was symmetric at one. You didn't have the choice to choose a vacuum to live in. But then after inflation, like the phase cooled down, and effectively the vacuum kind of was displaced from this minima, and the vacuum was restarted on it. So instead of a perfectly quadratic shape, you had some kind of bump in it. So your universe was here. It had a choice to go either way, and it moved to the positive end, and we had a small positive cosmological constant. That's not right. So this is the idea of spontaneous symmetry breaking is inherently related to cosmology, but at the large scale, but also at a very small scale of particle physics. Right? So this is where I will continue from in the next and last lecture, where we'll look at the spontaneous broken symmetry giving rise to mass to particles in the standard mode and by the Higgs mechanism. Right? Okay.